Hi again. In this video, we are now going to look specifically at reactions of our carboxylic acid derivatives, and we are going to start with hydrolysis. So for hydrolysis, actually before we start, why don't we remind ourselves about how the ski slope looks like. The ski slope again shows you the order or the reactivities of our four main derivatives, and our first reaction is all of these red arrows going back to the carboxylic acid. Not only do you want to remind yourself of your ski slope, but you do want to remind yourself of which derivatives are more reactive. And we're going to consider these first two more reactive than these bottom two. Esters and amides need help in their reaction, typically through acid catalysis. Okay, reaction A. If you don't have this was from the last video, 06A50. If you don't have this chart or this roadmap, go ahead and pause the video and copy it. Again, we're going to fill in all the red arrows first. Hydrolysis. As a reminder, you could think of hydrolysis as you could use water to lyse your molecule. And we are going to take all four derivatives and do hydrolysis. The first derivative was an acid chloride, and because acid chlorides are pretty reactive, you don't need any help. You don't need any acid catalysis. All you need is just water. And your product is going to be the carboxylic acid. And I normally don't, if it's on an exam and I ask you to fill in the product, I normally don't expect the secondary products or the products that aren't organic compounds. But here we get HCl. Cl was the leaving group, but it eventually removed the hydrogen from the water that attacked. We'll do some of the mechanisms, not all, but that's fine because a lot of the mechanisms are analogous to each other. Let's take the anhydride. Anhydrides are fairly reactive also, and it follows that all you need is water here as well. Okay, practice drawing your product. I'm going to attack the carbon on the left. It's symmetrical, so it doesn't matter which carbon, but it's fine. You could put a dotted line to show what's your leaving group. Eventually, that leaving group is going to strip off a hydrogen off of the water that attacked. So, in this case, we have the same carboxylic acid plus our leaving group that got protonated by removing the second hydrogen off of water. So that's why this is an OH. This is an OH because this oxygen grabbed the proton. It's symmetrical, and we actually get two carboxylic acids, and because the molecule in anhydride that we started out with was symmetrical, we get two of the same. We could say that these are identical, or we should say these are identical, and I'll put an I. Next comes an ester. If you understood, I think it was unit 5, the carboxylic acid unit, if you understood how to make an ester via a carboxylic acid, this will look very familiar, except it's backwards. So here we're going to have water, and because it's a little bit more robust, less reactive than an acid chloride and an anhydride, we're going to use some acid, and we could use H2O plus, or we could just add hydrochloric acid, same difference. Let's put our dot. Let's put our dotted line. Same carboxylic acid, because we're matching the carbons on the left, plus that alkoxide, that looks like the leaving group actually left as an alcohol. Remember what this is? Carboxylic acid plus alcohol going in the reverse direction is Fischer esterification. This is the reverse of Fischer esterification. Hopefully I told you when we looked over Fischer esterification and did the mechanism, that I told you that this is reversible. There were a bunch of equilibrium errors throughout that mechanism. Reverse of Fischer esterification. What does that mean? If you know Fischer esterification well, the mechanism, then you just reverse it to hydrolyze the ester back to its carboxylic acid and alcohol. The last one is an amide, and probably I'll do the mechanism for the amide. It is the most stable, which means it's very hard to hydrolyze this. And you're going to hydrolyze with water again, but now we're going to use very, very concentrated HCl, and we'll indicate that with the big M. That stands for molarity, 6 molar. 6 is the molarity, but you pronounce it 6 molar HCl. And this one is a little bit trickier. We're still going to get the carboxylic acid. Okay? You're still going to attack that dot eventually, and eventually kick out this group here. The thing is, what would you have predicted? You would have predicted that instead of NH minus, you would get NH2. It picks up another proton. Just like we don't have O minus here, it picks up a proton. Just like we don't have the carboxylate, the O minus there, it picks up a proton. We don't get an N minus, we picked up a proton. The problem here is that this is called an amine, and amines are actually pretty basic. We talked about ammonia being pretty basic. Well, you're under acidic conditions, so you're not going to end up with just NH2. That NH2 is going to grab another proton and become NH3+. I have a plus there already. NH3. So nitrogen with 4 bonds and no lone pairs is positive. Are we worried about balancing? No, you have a lot of HCl. Okay, so if you wanted to balance, maybe you'll have a Cl minus, the counter ion. But I think, well, I know that when I ask for the products for hydrolysis, I am probably going to remind my students that I do want the secondary product. I do want the part that left, the leaving group. And when you draw the leaving group of an amide hydrolysis, you have to make sure that that amine is protonated. Okay. Actually, let's take that 5th beetle, right? The nitrile. Nitrile is always, not always, is also pretty stable. Okay. And I'm going to use, again, 6 molar HCl. Where do I cut? Where's my pink line? Well, my dot actually is this carbon. So the pink dotted line is next to the dot. I'm not going to do the mechanism unless I have a lot of time at the end of this reaction. You have 3 carbons, 1, 2, 3. You can hydrolyze a nitrile into the carboxylic acid. And what was the leaving group? The leaving group is actually NH4 now. It's a protonated amine, in this case ammonia, because we're under acidic conditions. If you want, we can remind ourselves what the class of molecules are. Nitrile, amide, ester, anhydride, acid chloride. Mechanism. I'm going to show you the mechanism. I'll put an M with a circle. Let me put it under the arrow. That way, At least for my class, there's no confusion that you need to know this mechanism. Now the thing is, it will be a lot of reactions, a lot of mechanisms, but they're all analogous to each other. We just have to remember, are we going to protonate or not? And if your derivatives are pretty reactive, you don't need to protonate. Okay? No acid. But if you're an ester or amide, you do want to protonate. Easy. Let's do acid chloride. Whatever I do with acid chloride mechanism, you're going to do the same mechanism for the anhydride. We have a direct attack because acid chlorides and anhydrides are very reactive. I'm going to attack with water. I'm going to write water backwards. It's still water. Keep doing that. Here's your dot. Reactive enough that we don't need to protonate the oxygen. Okay, and this is important. You don't kick out the leaving group right away. You make what's called a tetrahedral intermediate in all cases. Tetrahedral. So have the chlorine. Still have this water. Oh no, we're good. So this is the tetrahedral intermediate. And it really does form. But it's short-lived because what's going to happen is we're going to bring this down and we're going to kick out the chlorine. We've seen this before where we have to decide what we want to do first. Do we want to neutralize the molecule by, at least this part of the molecule, by removing the proton, or do you want to collapse the lone pair to remake the double bond and kick out the leaving group? This happens fairly readily, so we do that first. And we have, oh, I think we have it already. Oh no, we don't. We almost have that carboxylic acid. And we kicked out chloride. Grab that hydrogen. Draw your products. Is there anything else that we forgot? I don't think so. Now, that is the mechanism. 1, 2, 3 steps. If you had the anhydride, okay, I told you it's the same mechanism, just now your leaving group's different, but the same pathway. You attack with water. Oh, let me show you from here. You attack with water, form the tetrahedral intermediate. When you remake the double bond, you kick out this group, the carboxylate. Just like here, we kicked out the chloride. Now that chloride in this case, or the carboxylate in the anhydride case, will come back, grab that hydrogen, and you're done. So you should know, you should practice, go through the mechanism for this one here. Now let me show you what happens with acid catalysis. We need acid catalysis for an ester and amide because they're not as reactive as the acid chloride and anhydride. We discussed the reactivities and why, or tried to explain why amides are not as reactive as acid chlorides. You could always go back to that first video. Let's do the amide. The amide looks like this. Amide to use. Not very reactive, so we are going to protonate. You could protonate with H2O plus. You know, water plus HCl will give you H2O plus. I'm going to say that we have a lot of acid, and we'll have some of the HCl available for us to do this. That's already different from the mechanism we just saw. We didn't protonate first. Okay, we have this. What does this accomplish? It makes that carbon more electrophilic. Don't forget what we're trying to do. We're trying to add water to break some bonds. We make chloride. I'll just put that. Here's water. Attack the dot. Pick up the pi bond. Hopefully this is not foreign to you. I mean, we've never done the mechanism together, but this idea that you activate the C double bond oxygen, the idea that right after that you use a nucleophile to attack, always keeping your eye on the target. The target is to get a carboxylic acid and kick out this nitrogen group. We form the tetrahedral intermediate again. Tetrahedral intermediate. Now, we have this. Sorry. Okay. I'm going to neutralize this part of the molecule. Some professors will say, well, if I know I'm going to kick out this group, why don't I protonate this nitrogen by deprotonating this at the same time? Some professors are adverse to that. Some professors allow you to do that. I'm not adverse to it, but in actuality, your proton transfer is not typically intramolecular. It's through the solvent or through some other intermediary molecule. I gotta look at something. Oh yeah, we're doing hydrolysis. We're in water. So here's your water, and we neutralize everything. Yes, this is longer because we do have a lot of proton transfers. What do we not do? What do we need to kick out? We need to kick out that group here, the NH methyl. We did create acid in the form of hydronium. And why don't we protonate this, make it a better leaving group. N minus is not a good leaving group, but N neutral, not an N neutral. That's a good question. Let me just think about it. Yeah, N neutral. There, this is what I'm thinking. Now our nitrogen is positively charged. We still have this OH down here. We did create water, but we're not going to use it. To kick out this group, we're going to use what I call the internal lone pair. We're going to remake a double bond, or make the double bond, and kick it out. The temptation is to use a nucleophile from outside the molecule to come in and kick this out, but that doesn't get us near the product. Our product only has 2 oxygens, the carboxylic acid. And also in actuality, this is what happens. Because you can isolate this. It's pretty short-lived though. See where we got the double bond? And then we did kick out, oh, this is convenient. We did kick out this ammonia, not ammonia, methyl amine. It's an amine. This was fortuitous because when we talked about hydrolysis of an amide in the overall reaction, I said that the amines are acidic. The amines are basic, and it will grab the proton of the acid. It's fortuitous because that hydrogen is pretty acidic. That really wants to come off and make that oxygen neutral. So we could do that right away. We don't have to grab it from hydronium. Kills 2 birds with 1 stone. Right? We protonate and we deprotonate. All right, that's different, right, than doing something intramolecular. Okay? We could have skipped a step and get the nitrogen protonated by just grabbing this hydrogen from here. That's not what happens. In this case, yeah, we're using an outside molecule. Grab the hydrogen and If you could do this, hydrolysis of an amide under acidic conditions, you can do acid hydrolysis of an ester. Okay? So we did two mechanisms together. We did, mark it up. We did the first one, and we did the fourth one, the last one. You should be able to do the other two, based on the idea that esters react like amides and anhydrides react like acid chlorides. The next section is with alcohols. Okay, not water, but with alcohol. So instead of water here, we're going to have alcohol, and we are going to follow this pattern where we need some catalysis for the derivatives that don't react very easily. I might take that back. But let's start with reaction B now. Okay, I am grouping, right? Reaction A is hydrolysis, but we're doing hydrolysis on all the derivatives, 5 different derivatives actually. Addition of alcohol is the same deal. We're going to look at all derivatives except for nitrile. Nitrile, you don't typically react with alcohols. I don't think a reaction would happen with alcohols, actually. So here we have reaction with alcohols. I might have to go through this a little bit faster than I want. But the thing is, it's analogous to what we did with water. So let me make sure that we at least get the examples up. The alcohol that I want to use is this. Sometimes they use base, but it's not necessary. These are pretty reactive. And what do? You want to match, you want to pretend that the alcohol comes in, kicks out the chlorine, and we get the ester. This is what I mean by interconversion. If you look at your ski slope, what did we just do? We went from the acid chloride to the ester. Acid chloride to the ester. Do I want to make do I want to draw the leaving group? Sure. Acid chloride to the ester. Well, what if we have an anhydride? What do you think we get? If I react it with the same alcohol, again, pretend that that alcohol comes in, hits this dot, make the tetrahedral intermediate, but eventually you kick out the leaving group. So here we make the ester from the anhydride. What was the leaving group? The leaving group is this carboxylic acid. See what's happening? So, see this bond right here was made. There's your alcohol part that attacked. This bond was made. So you're making an ester, it seems like, every time. Now, if you take a look at the map, now what's happening is we went from acid chloride using this longer purple line to ester, and then we did acid anhydride to ester. You could do ester to ester. That's called transesterification. But yes, we normally, and I'm not going to show you, we normally don't go from amide to ester. We do not go uphill without taking the ski lift. Let me get those reactions in. So here we have an ester. I'm going to use this ester. Methyl ester. Let me label these. And we're going to form another ester by switching out this alkoxy group with a new alkoxy group, in this case, a ethyl group. Now, I'm trying to figure out whether we want to use any catalysis here. Honestly, you could do transfer esterification fairly readily without acid, but I am going to add a little bit of heat to push the reaction a little bit faster. And we get this. The alkoxy group, right? This came in, we made this leave by protonating it. So our leaving group now looks like this piece right here that's been protonated. And then I will just put here the amide and say no reaction. Or I would say don't try to make an ester from an amide directly. Again, what you can do is you could hydrolyze that amide to the carboxylic acid. Okay, so here's our starting image on my left finger. Then we go to the acid chloride, and then we take a purple line down to the ester. That's the way that you go from amide to ester. You have to go through those 3 reactions. 1, 2, 3. I'm going to put in here a little note. I'm not going to say no reaction. Instead, I'll say don't even try. Don't try to make ester directly from amide. In terms of mechanism, we have time. There's no acid catalysis in these 3, so why don't we show you? Let me do the anhydride. Okay, but again, if you know the anhydride, you know the other 2. Heck, if you know your hydrolysis, you know this already. Let me show you the anhydride. Even it looks when it's kicked out. Okay. Then a anhydride, was it symmetrical? Yeah, it's symmetrical. And no acid catalysis, just go ahead and attack. And I'm going to attack the carbon on the left. You could have attacked the carbon on the right if you wanted. Form the tetrahedral intermediate. We're going to have that question, do we make it neutral? Do we make the intermediate neutral? Or do we remake the double bond? Let me show you what I'm talking about. Here's your tetrahedral intermediate. That's your tetrahedral intermediate. Do we get rid of this hydrogen next, or do we make the double bond? Just like we did with the acid chloride and hydrolysis, go ahead and kick out the leaving group. Look what we have. I think this is going to be very helpful. We still have this alkoxy group. It's methyl. Oh, sorry, it's ethyl. See, I'm drawing this piece now here. But look what we kicked out. We kicked out an anion, which is great because we're going to use that anion to deprotonate, and that will complete the mechanism. Right there. Anhydride to ester. Before I end this video, what have we accomplished? It may not seem like it, that we accomplished this much, but we accomplished a lot. We took care of all the red arrows. Okay? We didn't do the mechanism for this, but we showed how to do this with 6 molar HCl. We took care of all the red arrows. Those are hydrolysis. For the purple arrows, we took care of acid chloride to ester. The mechanism was anhydride to ester. That's it. Right? Oh, and we did transfer esterification. Like a purple arrow goes from ester to ester. We're going to fill in the rest of the purple arrows, plus a couple more in the next couple of videos.